My name is Yue Li. I'm a co-founder, CTO of MemVerge. Very glad to present our results and what we found, what we have here. So in my part, so I will basically, since this is an AI field day, so we'll basically mainly focus on our explorations on machine learning use cases together with memory machine software. So the machine learning basically has two major components here, as everyone is familiar with. The first one is the training. The second one is inference or model serving. So, and we found actually that for both cases, there are interesting applications, interesting use cases where that requires lots of memory. And we think that we have done some work to show that we can help with those workloads. So just we'll briefly discuss the results we have on each of these aspects. So first we'll start with training, because without training, there's no way to serve the models. So we found that for some of the trainings, machine learning, they actually do, today we're already seeing that they start requiring more and more memories. So for example, just a few examples here. So like, for example, recommendation engines for, hyperscaler for like social networks. So they typically require loading a huge amount of user data as a training data. And they need to try to fit in those data as much as they can into the memory so that they can do efficient computations. So just think, when you look at this large data set, think about, the data set that the Facebook has or LinkedIn has. So this is huge. And also another cool example is that recently the natural language processing community has pushed out this GPT-3, which really has 175 billion parameters, which is about more than 700 gigabytes in memory data size. And also when they do the training, the batch size is actually 3.2 million records. That's huge. And if you look at the paper, you can see that first of all, the model is too large to be made available to the public. And the second is very hard to reproduce for individuals, because there's no such expensive resource to use to compute. So for such kind of trainings that requires lots of memories, there are already lots of existing solutions. For example, the most intuitive one is, of course, if you run out of memory, just use some disk like SSDs to serve as a swap, right? Just create a swap file and write to the swap file. And then, of course, the more advanced solution that all those hyperscalers are using is using distributed training, right? You use many servers so that you can leverage the memories from all these servers and just cut the problem into pieces and fit them individually into different machines' memory. So the limitations for this, we actually talk with lots of machine learning experts from our customers or from our collaborators. And we found basically there are many limitations of these approaches. Of course, if you do swap, it's very slow, right? So we're always trying to avoid using a swap because it's just the algorithm is not efficient enough. And if you use distributed training, that's the major solutions here. And it requires many nodes. You requires high-speed networks. It also requires, external storage arrays, for example, to store the data, share the data between those servers. So it's a very heavy infra, and that could be very costly. And of course, once you make this distributed, then the network overhead cannot be ignored, right? And furthermore, for distributed training, another issue is that once you have the distributed training workers running, some workers may be slower in training, and some workers actually may be faster. So the faster ones are always generating better models, and the slower one is also trying to bring the older models back to the new models. So it's trying to polluting the models. So in this case, it might actually affect the accuracy. And in some cases, we learned from our customer, some distributed training even cannot converge due to this kind of inconsistency on the performance between different nodes. So if you talk with we talk with many machine learning experts, and they all told me that they prefer, if they can, trying to just use a single node, single box, and feed everything into the memory and start training there. And that would be make the life much easier. So, our solution for this motivation or this problem is that, as Charles mentioned, a memory machine actually can combine the DRAM and PMEM together to provide very large memory and with DRAM-like speed on a single machines. Today it's a single machine. Yeah. Yes.
A lot of the training nowadays is being done in GPUs, which have their own DRAM and that sort of thing. How does this play into that space? Because you're not expending or extending GPU DRAM at all, right?
Correct. We are still at the host memory. So basically, we're serving as a source for the GPU memory, because GPU memory, they still have to swap the memory between the GPU memory and the host memory. But we have to first stage the data into the host memory. So there's still a significant amount of use of the host memory for machine learning today.
Okay, thanks.
So within GPU, there are HBM, high bandwidth memory, and those are faster and usually smaller in availability. So they even in the GPU machines, the main DRAM is still being extensively used, and our main value prop is to increase the size and the performance of that main memory.
Yes. So on the other side, there's of course deep learning can benefit from GPUs, and there's a large set of workloads that actually cannot be benefited from using GPUs. And there are lots of big workloads, a set of workloads that actually still running on CPUs that does not have GPU. And for us, we just the first motivation is just to provide large memory to let the machines or the workloads to continue training and trying to fit as much data as they can into the memory to accelerate their performance. And what we are especially looking at in this exploration is trying to look for those memory intensive workloads and trying to evaluate the performance by comparing using DRAM only and comparing with the performance on using memory machines. So one example I want to discuss in this presentation is, first of all, we met this actually from a customer POC. It's called GraphSage. So it's an open source algorithm invented by a professor at Stanford in 2017. It is a very popular graph convolutional network algorithm, and it's popular due to its great performance. And it shows that actually the accuracy of these models is actually outperforming the state-of-the-art performance. It's already made open source. You can use this in TensorFlow and PyTorch. We look at the TensorFlow version. And the application basically is in actually the recommendation engines for social network. So if you look at the existing work, so multiple network internet companies are actually testing this, and in particular, Pinterest has actually already make this GraphSage in production. So they actually had a paper on that. It's called, I think, called PinSage. Well, so what is interesting about this workload is that actually when it starts training, so you actually taking all the training data into the memory and build up this network. So let's say you have a social network that let's say, for example, LinkedIn or Facebook, you're connecting different people or different jobs or companies. They actually needs to taking all these data, put them into the memory and construct the in-memory graph to basically represent that data. And that graph, you can see that in real production, it can be huge, right? So for example, in a custom POC, training on 10 million nodes, representing a special area of the users, needs more than 1 terabyte memory. So
something like Facebook would require, with 5 billion users or something like that, would require 100 500 times this sort of thing. Is that for the memory?
So yeah, so actually the way they do it is actually using distributed training. They have to cut them into small.
They have to cut it. Yeah. I understand. Yeah, okay, thanks.
Right. So we were testing in this POC. So we are trying to testing the same workload with the memory machines, transparent memory service, essentially trying to allocate memory from this two-tiered memory. So just to reiterate some of the features that we have. So we the transparent memory service trying to provide memory management that is optimized for persistent memory. And we also everything is software defined, meaning that you can configure the DRAM tier size to accelerate the PMAM for different workload. You say for application 1, I don't want DRAM at all because I think it's a testing, or it doesn't need performance. For the second training workloads, you might actually configure more DRAM tiers so that you can accelerate the training better, but still enjoying a larger memory. And the total capacity here they see is actually DRAM plus PMAM. So this total capacity, will become much larger. And furthermore, so we are using the persistent memory's AppDirect mode. So that means that we still have the persistence being kept for these workloads. So I will mention one use case later. Basically, user can actually persist their in-memory models instantaneously, and they can, just as Charles mentioned, we can snapshot the models, and then we can restart the model or restart the serving a large model in memory instantaneously. On the other side, also we do offer quite a bit of flexibility and make it very easy to use. The first thing is that the user can run run their training or inference on top of us without any code change. So they don't need to change any applications. We just but just directly allocate memory from us. The second way, as Charles also mentioned, is that if is an advanced developer, they can use our APIs, memory service APIs. So with these APIs, you can basically precisely place your data in the correct memory tier. So let's say you really know that this piece of data needs to have DRAM latency, then you can actually use our API to explicitly say that don't move it to PMAM. And you can also, for this code data, you can actually allocate them only in PMAM without having them to be promoted to the DRAM tier. But with the first approach, everything's automatic. We'll handle the page temperatures, and based on temperature, we'll start moving the page between the DRAM and PMAM. And also with the APIs, you will also be able to actually snapshot their the in-memory data structures that they allocated. All right, so just before showing the testing result, just here's the evaluation setup we had. So we are comparing the transparent memory service with the baseline. So for the baseline here, it's a single node comparison. It uses the DRAM first. So once it used up the DRAM, it will use the NVMe SSD as a swap. So the workload we tried is basically open source the graph stage using TensorFlow. And it uses a synthetic graph data that emulates a relatively larger testing data set. The total nodes is 250K. The node degree is 100. So this is probably too specific to this workload. And what we are trying to measure or compare is the time that's spent on different stages of the whole training process. So there's a stage for loading the data, the stage for training, computing, and the stage for writing the data back to our storage. So we compare all these stages, and so the platform we're using is actually a Cascade Lake CPUs and with 192 gigabyte DRAM, one NVMe SSDs as a swap, and there's a 12 Intel Optane PMAM used as in AppDirect mode that managed by our software. So this machine, this graph stage actually is able to leverage the GPUs. So on this server, it has 4 NVIDIA Tesla V100 GPUs there. So here are the results. So the yellow ones for the baseline, and the gray ones or the blue ones is for our results. The y-axis is the completion time of each stages in minutes. You can see that in total, there are 3 stages: graph loading. So it's essentially loading all the training data and building this graph data structures. And this is actually the most memory consuming part actually for the whole process, actually building the huge graph inside the memory. Then it starts training by iterating, by traversing this graphs and compute the parameters, the edge parameters, and so on and so forth. And after they finish the training, figuring all the parameters of the edges, it will start saving the models back to the storage. So you can see that with our approach, basically we're trying, by providing larger memory, we're able to basically allow this data to fully fit in the memory, so that we will be able to avoid the swapping. So for the data size here, so the data size after fully loading the memory, the data into the memory, the total data size is about twice of the DRAM size, so that the swap cannot be avoided in these cases. So with us, where there's no swap at all, so that's why you can see that in general we can basically for the baseline, the total cost is about 100 minutes, and for us it's 58 minutes. So here is another basically data on the memory consumptions for this workload when we're monitoring the memory consumptions when we're running this. And you can see that on the left-hand side is the baseline, right-hand side is our memory consumptions. And for the left-hand side, we are monitoring the DRAM consumption. And you can see that at the very beginning when it starts training, right? So the memory suddenly goes up to the top, because this is actually the first stage of the graph loading. Then you can see once the memory starts running out, right? The swap size starts kicking up, because this is because just the memory runs out, we start using the swap and so on. And finally, it gets stable, and then once the training is finished, then everything goes to zero. And similarly for us, you can see that the graph on the right-hand side is very interesting, that we only monitor, so there's no swap being used here. So we only monitor the DRAM and the PMEM. You see that similar at the very beginning, the DRAM goes up, right? Once it used up all the DRAM, and the PMEM capacity goes up, because now we start using the PMEM as well. And you can see that also in the period, in the last few 30 minutes or so, right? The DRAM capacity goes down. This is because there's a significant amount of data in the DRAM, actually is the code data. So in our algorithm, we actually migrate those code data back to the PMEM. So that's why you see that the PMEM consumption starts increasing. Right? So then finally, so that this all goes to zero. Right? But the main reason we are better is that basically we're avoiding swap, and the PMEM actually has better performance, in better latencies than NVMe SSDs, if you want to use it really as a memory. Okay, just let me know if you have any questions. So we're moving to the other component, which is the inference. Inference typically is deal with a real-time results. So imagine that you are doing the advertisement recommendation, so on, right? So this require to be real-time and low latency. So so ideal solutions also is widely practiced in industries. They trying to put almost all these features, models into memory or in-memory databases or into the memory, so that actually the access latency is very low, and they can provide the answers in tens of milliseconds. Right? But so with this approach, the limitation, of course, is that you have to use lots of DRAM, right? Think about how much features for, let's say, for Facebook or LinkedIn they have to put into the memory, right? That's huge, and there's a lot of DRAM there. And also, if you put lots of things in DRAM, once there's a crash, right? So reloading those back to the DRAM will take a very long time, because you have to visit storage and do that again. So for us, I think our solution again is just first of all to provide a cheaper but larger memory tier to hold more data, essentially to hold more features, more embedding tables and models into the memory. So first to reduce the cost, right? And then with that case, then you can basically you can also, it's possible for the customers to reduce the number of servers they use, so they no longer need to be doing this distributed, or they can just use some single node to fitting all these models. And using this single node to the machine model serving is actually very, very common. And the customers sometimes use actually really large DRAM servers to do that. So one example I want to show is basically we test one thing we test is the Facebook's DLRM. It's a deep learning recommendation model, and in this model, it basically to serve this model, it contains, as you see, this is a picture from their paper, and you can see that in this picture, it says that there's multiple components. There's sparse features, there's dense features. They all need to load them into the memory. And they said, you can see in this paper, they mentioned this one is memory capacity dominated, and the other one is memory bandwidth dominated. So clearly, this is actually a very memory hungry workload for real productions. So we evaluate this algorithm, and by comparing us with essentially by with the baseline using DRAM and DRAM only or use DRAM plus storage. Our solution is trying to basically put the models and the embedding tables, those are the features, into DRAM plus PMEM tier, and compare with the two baseline. The first baseline is trying to put everything in DRAM, and the second one is using DRAM plus NVMe SSDs, where they trying to put code data or the embedding tables only on the NVMe as key value stores. And you can see that the left-hand side, the blue bars basically represent the solution where you try to put everything in DRAM. Of course, the performance is fast when the data size, x-axis is the data size, is smaller. But when the data size actually approach the memory limit of this server, then you start using swap, and the performance suddenly becomes very bad, and it's become as bad as the solution, the storage-based solution. And if you're able to actually fitting all the data in the DRAM plus PMEM, you can see that the performance is really, really stable when the data size becomes larger and larger. So the orange bars basically represents our performance. Okay. All right. So basically, the other example is basically the image recognition workload we actually tested with another customer. So this one, in this workload, the customer is previously trying to put all the user features in MongoDB and trying to create a DRAM cache so that to load a small subset of the hard data of the MongoDB's data set. So in our test, we basically replace those two tiers with a DRAM plus PMEM tier and trying to fit all the data in MongoDB in memory. And once we do that, you can see that the gray bars here represent the previous performance of the baseline. And once we do that in memory, suddenly we have much higher throughput, and we have much lower latencies. Right? Latency is basically a few magnitudes difference in terms of latency, because by just simply avoid accessing the storage. Okay. So that's basically kind of like it's about what we have for the inference. So the other things we had is actually we can use persistent memory to actually take a snapshot of the models. Let's say you are pushing out different model and trying to see which one is more accurate. So one way is that you can use storage to keep on loading the new model from storage to construct new model serving applications and trying to test their accuracy. But if the model is too large, this test is very, very difficult, because then it requires a remote storage, and the storage and the networking could be slow. And for us, we just can take a snapshot of model serving of different models inside memory, and we can restart the model serving within less than 1 second in place, because the snapshot of the model serving is already in the memory. So we don't actually need to visit the storage again. So this allows you to roll back or recover a model. If the current new model doesn't work well, you can roll back and recover an older model that works well instantaneously without reloading everything back from the disk or external storage system. So that summarizes my part in this presentation. So in general, we think memory machines provides larger and cheaper heterogeneous memory infrastructure to accelerate the training and inference for machine learning. And we can use persistent memory for instant model snapshot and recovery. And again, there's no application chain is needed for many of those workloads. So intuitively, today, the human reasons everything fully actually from memory. So I think for machine learning, it will be the same in the era of the big memories that led by the persistent memory and the other new memory technologies.